wonderful tour de force, as always, from Jamie. And I'm really one of a couple of empiricists who are going to talk at this meeting, so I'm very much representing James Wood, and I'm also sort of here to talk about some of the other ways, some of the ways we empiricists see it. I also want you to be aware that we're much cleverer than we appear, really, and don't be fooled by the way we look. We are really quite sharp. So, for example, it was my objective at the last meeting to try and impress Valerie Isham. And I realized quite early on that Valerie would never be impressed by my research, and so my main product at the last meeting was the production of the t-shirt. And now I have a fantastic citation where Valerie refers to the t-shirt, so I feel as though I'm making it. The other product, of course, that came out of that meeting was this fantastic book, the Grenfell and Dobson book. And that was, actually I just realized I've misspelt Whither there, haven't I, James, again? Yes. So James and I were just having a discussion before this about what the title of this talk really should be. And anybody who doesn't know much Old English wouldn't know that a wether is actually a castrated old ram. And so we thought that there were quite a lot of similarities to. That's the correct spelling, isn't it, James? That is the correct. And that, you know, while Jamie had called our talk "Weather, Disease, Ecology," and he's obviously the new solution, I'm the old problem. So I have to say that this book that Brian and Andy produced really was a fantastic foundation for our understanding of wildlife diseases. I was always a bit disappointed, I have to admit, and it's the first time I've ever done this publicly, but in the Anderson and May book, I remember looking forward to that so much, and I was a little bit disappointed in it. This book, on the other hand, really did give us a foundation of where we are in the, particularly with the mean field models. And how have things changed since then? Well, I would say the main answer has been in data. At that stage, we hardly had any data. The data we had was just a ripple on the sea of disease ecology. And now we've been through several storms. We're getting multiple amounts of data, and it's clear from Ollie's talk and others' talks that we have a veritable tsunami coming towards us. And I can see into the future that the way that we're going to be funded is we're going to have to fit models to our data to test our parsimonious explanations, and then we're going to write our grants to identify the killer experiments and how important those killer experiments are. And as you probably realize by now, Otto has lent me the Norwegian soapbox, and I'm about to stand on my Norwegian soapbox and start talking about the importance of experiments. Before I get there, I just wanted to say that I shared a room with Andy, and at that stage I was working on nothing but the grouse work. Far beyond me, perhaps I'm looking at it the wrong way around. Anyway, Andy and I collaborated, we did a number of things, and we looked on the grouse work, and since then our collaborations have sparked into a number of different things, and we're now working on pathogens in wolves, in mice, in rats, and we're looking in Africa, in Madagascar, and we're also, I'm pleased to say, still working on sheep, and it's good that these old castrated sheep do that. So the key point, and the very important point I want to make, is to come up and talk about vaccinating with lemons. I want to talk about how we can save America, really, by eating more citrus fruit. So if you look, there's a very good relationship between the total US highway fatality rate and the amount of fresh lemons that are imported into USA from Mexico. This is a really good, very good relationship, and it doesn't take much of a very simple model to say if we imported 4,500 tons of lemons per annum, we could quite easily eradicate all highway fatalities in the US. And this really only means that in America, each American, 1 in 10 Americans must eat lemons. The whole point here, of course, is that this is a spurious correlation. And a spurious correlation never proves about cause and effect. And it's part of what the empiricists in the audience want to see, which are the mechanistic models that really get to grips with what is taking place. And the models themselves are still only hypotheses, which we really must go out and test rigorously. The approach that Andy and I were taking 20 years ago was we were developing the Anderson and May model. We were applying it to what happens in grouse. The main question we asked is why do grouse populations cycle? And the important component was whether parasites reduce fecundity. At that stage, we just produced a paper which had done a series of experiments. This must work. Did you have it work, Jamie? The pointer? Oh, there we go. Yeah. So we did a series of experiments. These are the results from the experiment. These are the controls. This was our correlation. We were able to show that that correlation was one of cause and effect. And while we were here, we developed on this model in the grouse populations to explain what actually caused the cycle, and from this designed experiments to go up a scale and to stop the fluctuations in grouse numbers. This has proved to be remarkably useful to the grouse moor owners, particularly those in northern England, where they have effectively applied the techniques and the solutions we developed from this model and stopped population crashes in grouse. Now, you probably don't care too much about that, but to them it's very important for finances and for this flow of money. It brings a lot of money into impoverished parts of the United Kingdom. And it's been a remarkable success. The parasite is almost extinct from northern England. And did you know it's almost impossible to sell corpses of grouse this year? And if you wanted to go and buy grouse, they're just giving them away because they have so many of them. And that was a consequence of our direct work up in that little room upstairs. We built on that. We sort of felt this relationship, this tight, intimate relationship between parasite and fecundity that led to unstable dynamics was just the core to understand the larger community effects. We subsequently went on, did food quality, predation, looked at other viral pathogens. So we did, Hans's talk was great. I was so impressed. He tried really well to show us a lot of data. And I was just so impressed that what I consider a theoretician just did such a fantastic job there. But we did do the killer experiments here, where we went out and manipulated those different terms and were able to show what actually took place and give us a greater understanding in the secondary and tertiary factors actually involved in this. The whole point here, of course, is that experiments are important. So if I turn round and start looking at the other hypotheses, and we have this dilution effect hypothesis. This is a really sexy hypothesis because it links biodiversity with the risk of exposure to zoonotic infections. And basically it's saying there's a negative relationship, so the more biodiversity you have, sorry about that, the more biodiversity you have, the less likely humans are to become infected. And that's a wonderful, wonderful hypothesis. So lots of conservation is good for human health. Save babies, look after a rhino. So it's all the sort of right sort of things we want to hear. The basic hypothesis is that there are competent and non-competent hosts in the system, what Jamie was calling the amplifiers. Was it? No. Yes. Maintenance. Yeah, anyway. I did listen. Non-competent hosts, and the idea is that the non-competent hosts are a sink to infection, and they sort of suck it all up. And it was during the 93 meeting that I talked a lot with Chris and people about wasted bites, and then started to investigate this. Since then, there's been a great deal of research on the dilution hypothesis, and much of it has been based in North America, and particularly on the Borrelia system that takes place there. The idea that Rick Osfeldt and Felicia Kiesing have come up with, and it's a good one, is that Ixodes is a vector of Borrelia, and really the mice are the competent hosts. There are other hosts in the system that suck up the wasted bites. These are the non-competent hosts, and if you remove biodiversity, then one consequence of that is the force of infection is then pushed towards humans. Therefore having biodiversity is very good. At this very meeting, I got involved with Mike Began and Roger Bowers, And we started talking about components of this, and what was then their student, Rachel Norman, did some models on this, and we subsequently went on and produced a paper which describes the ratio of density of competent hosts to non-competent hosts, and when the R0 for the virus and the R0 for the vector are greater than 1, and then when the virus would actually be absent. And indeed, I went on and did an experiment with my postdoc, Karen Lawrenson, to actually test this experimentally. But the whole point is that in this system, they should have done the experiment. Because the real problem, and I think the problem that Hans has with this, is they have generalized this concept and generalized it to say the competent hosts are the resilient hosts. The resilient hosts are the last individuals in a community when you start pulling out species. So the mice in this system certainly would be the resilient hosts. Those are the hosts that stay after you see fragmentation, after you see habitat degradation, because they like living with humans. The real problem is that this really can't be generalized. So what we need to do is a series of experiments. And I'm still shocked that this hasn't been done. And the first one is simply go and take the predictions from the Norman model, experimentally remove the competent hosts, and then as a negative control, you can come in and remove chipmunks. Relatively simple, straightforward experiment, and you could replicate it, randomize it, and do it in different parts of North America. There is an issue here which doesn't become obvious at first, but some of the data we've looked at indicates there are scale problems. And what you may see with an exclusion the size of this room would be very different from what you can expect to see at the size of a wood or the size of a state. And it brings me on to what my second point is going to be, which is about multiscalar problems. But the key point number one I want to make is neither correlations or models provide proof, and we really need perturbation experiments. We really need to identify the right sort of experiment to do. In that wonderful talk last night about smallpox, I was just stunned he didn't mention what I think was the killer experiment. The killer experiment was when Edward Jenner went and got his gardener's son, gave him cowpox to protect him, and then gave him smallpox to make sure he was protected. What a fantastic experiment to do. It was a wonderful experiment. Totally unethical, of course, but it was, if you've got a gardener's son, a very useful way to actually go and test the systems. So it's important that we think about it. We all do, or many of you are involved in what you see as vaccination trials or vaccination experiments, and of course you have problems with randomization and replication, but there's still perturbation experiments that can give us insight. And my main point, my first point, is that we really must be doing these types of experiments or interpreting them. Another, who wasn't as nice as Edward Jenner, not a very nice person at all, was Julius Jarrig. And here he is involved in doing an experiment. And in this experiment, he has this man here who has malaria, and he's transferring blood from this individual to this individual, and he has tertiary syphilis. You can see by the expression on his face, he's not particularly happy about this. But the whole idea was that you use malaria to give a fever to somebody who had syphilis. This would then kill the syphilis, and this fever effect would result in the removal of syphilis, which would be great. Leaves you with malaria, of course, but at least you got rid of the syphilis. Jarrig was not a very nice person, but he did win a Nobel Prize. I think it was the year after Ronald Ross got his, 1927, I think it was. Anyway, I'll look it up later, that would be quite interesting. The whole point here is it generated a hypothesis, and the hypothesis is that co-infections can influence transmission heterogeneities. And I'm going to talk a little bit more about that. The idea is that we need to go from what's happening within hosts through to what's actually happening between hosts. We need to ask the questions, what we have in the indirect competition, the immunomodulated effects that we see with pathogens in the host, how is that influencing transmission? How can we link what's happening at different scales within the host to the between host models. And I'm going to illustrate this with Isabella Catadori's very detailed study. I'm going to want to just show what she's done and what the opportunities are for being able to model it. So the first thing is she's chosen a system where she's looking at a huge proportion of the community. She's not only looking at Bordetella, which is a lung infection, myxoma and rabbit hemorrhagic disease virus. She's also looking at Cytitina, Moscovia, which are tapeworms. She's looking at Trichostrongylus and Graphidium, which are a stomach worm and a small intestine worm, and Pachyluris, which is it's the worm that you get in your bottom when oxyurid worm, which sticks in your bottom and why small boys scratch their bottoms, basically. The data she has is superb. She has 35 years of monthly data, which I think she must have started collecting the year she was born. She was collected monthly data on the intensity and presence of all these different pathogens. She's able to look at those as age intensity curves, so she's able to restructure from those and look at the age intensity curves and how those age intensity curves vary from year and on the month you're actually been born, and then she can look at the interactions. But I'm just going to start by looking at Trichostrongylus retortiformis, the interaction with Bordetella, and not get into too many of the other complexities. What she's then gone and done is she's gone back to the lab, she's set up lab experiments, and she's doing the within-host stuff in a very detailed way. She's able to produce what the immune pathways are, and she's been able to do that both in compartment 1, which is the local response, and compartment 2, which is the systemic response. Have I got that round the right way? I just suddenly think that. Yeah. No, I have, or it is round the right way. And she's done that for single infections in both the Bordetella and the Trichostrongylus. And then she looks to see where the interactions take place. So where are the common cytokines that interact between these two systems? And then she does that, and she can model that system. Then she can do a series of knockout experiments where she can go in and ask questions like, what happens when we knock out here IL-10? What happens to the Bordetella, IL-10? Well, it significantly reduces the Bordetella, and it also significantly reduces the Bordetella when the worm's present. In the worms in the Bordetella infection, when you look at the worms, it reduces the worms by about a third. So she's able to do all these experiments and make predictions about what she's going to see when she goes back in and does the more detailed experiments. She's building up a series of within-host models, and she's got fantastic data about what's actually taking place at the higher level. So by doing these small-scale experiments and things, she's starting to get some real insights in what is taking place. Now, what is the killer experiment she should now go and do? Well, the temptation is to go out and say, let's knock out one of these or several of these if we can. And that would, or even a functional group, if we could just go and knock out those groups in the wild and see if it's really affecting transmission and the dynamics of the other parasite. The key question here is the community important to understanding the dynamics of any one component species in this system? Now, several people are doing this in other systems, and they're doing it in mice, where they're applying ivermectin to try and control selective groups of parasites. It's the wrong experiment to do. It's a broad spectrum anthelmintic that is systemic, so it kills helminths, mites, bed bugs, lice, and ticks. It's sometimes toxic to some genotypes, and it can even stimulate an immune response. So that, I don't think, is the right experiment. So it leaves her with a position where what can she do to start elucidating it? Well, what she can do is rabbits have been taken and released in different parts of the country, parts of the world, I mean, obviously into New Zealand, Australia, and Tasmania. And that release of the rabbits has had a founding effect, so that not all the parasites, when they were taken from Great Britain and introduced over there, actually carried all the parasites with them. So she's actually now starting to study these to see what's taking place after these founder effects. So my second point is that co-infections could be important. We need to start investigating them. I think it's important, I think it's obvious from the previous talks this is the case, but could also, and she's demonstrated this, introduce important transmission heterogeneities, which may be very important for persistence. That brings me to my last point. At the last meeting, actually I was amazed, I timed you. You took 24 minutes to say R0, Hans, and I don't think I've ever been in conversation with you where you've gone as long as 24 minutes without saying R0. And congratulations. But I do worry that we get a bit too wrapped up with R0. It is a wonderful, what do you call it, Brian? You call it some enigmatic parameter, is that right? You call it sometimes. But it's wonderful for looking at initial spread. It's wonderful for looking at the likelihood of epidemic. It's immensely helpful for doing vaccination. But selection doesn't always maximize R0. And we know from several models by Gandon and people that things like superinfection and vertical transmission, you know, clearly the estimation of maximizing R0 doesn't work. So we need to think about alternative models and alternative hypotheses, and Jamie and I talked quite a lot about the whole persistence issue. And I am also of a great belief that we should start getting involved in that. I'm not going to repeat what Jamie said, but one thing that Brian did, I think it was back in 2002, is that he looked at differences in the dynamics where you keep the R0 the same, but basically you change the relative size of the transmission rate against the infectious period. And he showed very easily with a seasonally forced pathogen, which just happens to look a bit like measles, you can get very different dynamics. Likelihood of persistence as opposed to epidemic fade out is going to sort of change. So not the same R0 will give you the same result. I want to change gears slightly and talk about issues with persistence in simple direct monozemic life cycles in the nematodes. And the basic thing about this model, I'm watching the time and wear of tea, basic thing about this model is it's highly unstable. You get more likely to get epidemic fade out, and not surprisingly when you look at the animals, they have special adaptations to get over this. And Andy and I have done quite a bit of work, and we were working on this back in '93, about the whole issues of hyperbiosis, arrested development, where the worms, when they enter the host, actually go into a period of dormancy, where there's no mortality rate, but they just sit there, and it's like diapause in insects. But doing that effectively reduces your R0, but it does increase your likelihood of persistence. Indeed, if you look at the evolution of complex life cycles in general, what's probably taking place is that it's all about just trying to persist and making sure that you don't go through these very tight bottlenecks. On the other hand, Jeff Parker's a lovely man. I love what Jeff does, love his work, but all his research at the moment is about complex life cycle evolution, and so much of it is just based about maximizing R0. I think we really need the alternative hypotheses, and we've got to start testing our data against alternative hypotheses, and one of those is about persistence. So, I was just going to mention persistent mechanisms abound, and maybe even the multiple host system that we see in rabies is some sort of persistent mechanism. This comes back to Jamie's talk. And yet other neuroinfections such as chickenpox, shingles, is clearly another sort of persistent mechanism. So I've tried to make 3 points. The most important point is that we need to continue doing experiments. Even if you don't think you can do the killer experiment, design that killer experiment and tell us what you think it should be. And then if you can't do it for ethical reasons, say, this is the next best step. I think co-infections and the importance they are in generating heterogeneities really needs to be elucidated. Why were some of those SARS people clearly super spreaders and others not? We need to understand the within-host factors that are generating those heterogeneities. And lastly, I just wanted to emphasize that R naught is but one hypothesis, and we should be starting to think much more about persistence. Thank you, Julia. All questions will be answered by Jamie because he's the bright young thing, and I'm.
I very much like your talk there, and I very much agreed about talking about this dark matter. But I had a remark about one of your pictures, talking about bovine TBs. There's a big elephant in the room there. I mean, cows are infected a lot of times with bovine TB, and in many of these models, it's not considered. And I think if you really want to understand why it's persisting, you also should take the cows into account.
I'll take that. I will agree with that. Like where there's ecological contact with cows and cows are infected, they should certainly be in the thought model.
They are subcritical because of the control measures, human state, but I mean, that was also one of your points. Also those populations should be taken into account, and because there are lots of cows and lots of infections occurring in cows.
Yeah, I think that is an important point about the dark matter that I didn't have time to make. Is that our attention is typically focused on species that show conspicuous signs of infection. So you see outbreaks and die-offs and things like that. And very frequently, the true reservoirs are not showing conspicuous signs of infection. And Pete and I were chatting about this. It actually has been one of the definitions put forward for a reservoir, and actually something Hayden et al. Were pushing back against a bit to get the epidemiological dimension in. But it may well be time for us to sort of bring that idea back to the fore and integrate it with our understanding of the epidemiology. Because if there's any kind of generality to the statement that the true maintenance hosts frequently are silent carriers, then we've got real challenges. We've got to think about how to solve them.
Yeah, 2 points. First of all, that the experiment you want to do is you want to do the removal of the cows and then actually see if it persists. And you say, well, that can't sort of happen. But then foot and mouth gave us a beautiful way of actually looking at that. And I think the data, I don't know if they have been analysed that way, James, but they should be.
They've been presented empirically, but not really properly analysed and incorporated into two-host systems.
Yeah, so that's an I also, in some of the work that, and I've just come from Oregon, where Andy and I've got a great project looking at spillover and persistence of mycoplasma in bighorn sheep. And it's so clear to me that domestic sheep are the tolerant hosts, and the bighorn sheep are the resistant hosts, and they're suffering because of immunopathology. Now, I know Hayden and people didn't like that idea about why the reservoirs are often the why the reservoirs could be the tolerant host. But I still think that's something we should think more about.
On your last point about R naught, you're really saying, aren't you, that R naught is not the quantity that guarantees maximal reproductive fitness, because it's reproductive fitness that counts with respect to the kinds of individuals you see in future generations, right?
Yep.
So, well, I think everyone would agree, wouldn't they, that R
Well,
naught
it's
is not
what Jamie is calling replenishment rates, and I recognise that in his paper, because there's immigration issues as well there. So, in some instances we do have source sinks, where the pathogen locally can wipe it out, and then it's just, the pathogen could be kept down by immigration. But I get the point. Yes, you are.
Sorry, on your last point, I mean, no one ever said, I don't know of anyone who's ever said that the successful disease should make R naught as large as possible. It's all about, there's a threshold phenomenon, and R naught is a parameter which you rather tailor so that the critical value is 1 if possible, because that keeps life simple for us. It's like it's all de-dimensionalizing. But no, I think surely it's been well recognized for a long time that making R naught too high, it could kill everyone off in the first sort of outbreak, and so the disease doesn't persist. And it's the simplest sort of modelling example. I'm sure there'll be others.
So my point, perhaps I didn't say, my point was there are other hypotheses other than maximising R naught.
Yeah, well, what I'm saying is I think that I don't see maximising R naught as ever having been...
Optimising R naught would perhaps be a better way.
You think about it in an adaptive dynamic spirit.
In a what?
In the spirit of adaptive dynamics.
Yeah, okay.
Then it becomes clear that the only way to decide about it is to take into account the interaction. So the non-linearity in the system determines what will be the end result of evolution.
So I don't disagree with that, but I think Chris's point about replenishment rates and things are also part of that.
I think that's evidence of quite a lot of diseases, that possibly the successful disease makes R naught just comfortably bigger than 1,
Yes.
but it doesn't make it too high.
Well,
I'm sure it's not true of everything. But
ecologists used to talk about R and K selection.
Yeah,
And the R thing is the focus on R naught.
yeah.
And the K selection is
Yeah.
about living at equilibrium.
So Ollie's going to disagree.
No, I was going to bring up R and K selection. I thought it was slightly different to that, in that little r is, so it's intrinsic growth rate,
Yeah.
what Pianka was talking about, versus K, the carrying capacity, and that
Yeah.
those two things can often trade off against each other. And that, is there anything
No,
more than Pianka's theory and basically what you're saying? You're either kind of like a rapid spread of the short.
So I think R naught is usually geared towards establishment, and I think when we're looking at critical community size, and Jamie described it well, I've whizzed through that a bit at the end, but the critical community size is very much about the replenishment of the susceptibles.
I think people have conflated the two because R naught is a lifetime fecundity, and that has been commonly one definition of fitness used in the past. I just wondered if all the work on formal Darwinism, which is basically all about what exactly is it that natural selection is optimizing, could actually be of some use now in epidemiology, such as Alan Graffan and Andy Gardner and people like this. So they're also talking about multi-level selection, which of course we've got within-host evolution versus between-host evolution. It's rather unclear as to exactly what is the optimum.
Yeah, so I don't know the literature on formal Darwinism, but I think it's exactly this multi-level selection problem. And I think that may also be part of what drove Pete to, hang up this foil of optimizing R naught, maximizing R naught, being a focus for some people. Like you showed the one set of work that was explicitly oriented towards maximizing R naught. I do think that there are differences between R and K selection and this issue of persistence in certainly acute infectious diseases, and that has to do in many cases with things like overcompensating dynamics or other sort of non-stability in the dynamics, because R and K selection in simple form just has to do with having an aggressive, quick multiplying strategy versus being a long-term competitor. And it may encompass some of these non-stationary dimensions, but I think for infectious diseases, and certainly for the problems that I'm thinking of, and I think Pete, given the issues of seasonality for many infections and other things that sort of expose the population to troughs, they're different. I think the nature of the mechanisms that are important for persistence, such as these sort of dormant phases or occasional chronic carriers that enable you to get across those troughs, may have a disproportionate importance, which isn't part of the sort of the simple conception of case selection. With that said, I've always thought, and maybe someone here can actually do this, that there would be a lot of hay to be made in applying formal ideas from life history theory to this exact problem. And it's sort of what I was waving a hand at when I was saying that maybe there's some clever kernel methods that could be used to think about what's the impact of one host species having a generation time that is a host generation time that's an order of magnitude greater than the one that you're focusing on. Vincent, you look displeased.
Last point. It seems to me that a lot of that discussion about the optimization of R naught is coming from the evolutionary ecology literature, and simple models, indeed R naught is optimized. You would get the sort of things you get with formal Darwinism only if you get co-infection or super-infection, that you would get them easily. But I think in many cases that is not so relevant. But I think that whole idea comes from simple models that probably are too simple. In many cases it would not optimize, but in the majority you would see something like that, and I think that's where that idea is coming from.
I think a very key point that Ollie made is, I think multi-level selection is really a crucial element here.
But at that level, one of the important
levels would be the multiple infection of two strains within one host, and that often is not so relevant or overlooked. And I think that's an important discussion. But in order to get that would be the first thing I would like to assess whether that is really the case or not.
Okay, the point I was trying to make is that I think selection at the level of host populations or beyond may be the important thing for this long-term persistence. And this is the point that Pete made about sort of hot pathogen coming in and burning out its population, not having the patience, if you will, to make it to jump into another population and hence persist or to sort of survive through the trough. Anyway, good discussion.
And in wildlife, that can be that results in host selection, which is obviously not important in humans, but it's something that I really think we should be thinking much more about, particularly in the wildlife situation. I don't know about the veterinary situation.
It's halfway between the two, isn't it?
Yeah.
Just a reminder, after 2 we're going to have 2 talks, and after that, who's got a poster here? There should be 8 posters. If from each poster someone will come up and give a 67-second hook to persuade people to come and look at your poster. So that'll be after the next 2 talks.